Good afternoon, everyone. Thank you for coming. My name is Ray. I'm a PhD student at Penn State University, and today I'm very glad to present my work. And it is damage identification in concrete structures using the physics-informed neural networks. As we know, to ensure the safety of a structure like a concrete bridge, we need to continuously monitor the structure. It can be based on the vision, like the imagery with the cracking, and also it can be the vibration based, which means we can put some sensors to get the strain history or the accelerations to monitoring the system. So in that case, we can get a lot of that data. So it can be used a classic input and output system. So we can analyze this data by using some structural damage identification approaches to analyze this data, to identify the damage, and then to assess the condition of the structure. So based on whether we know exactly the model of the structure, it can divide in two parts. The first is based on the physics model, which means we have a detailed model of this system. For example, we can use a finite element modeling to create a detailed model. But it can be computationally expensive because when we get the sensor data, we need to update the model continuously. It can be computationally expensive. Another that is purely data-driven. So in that case, we don't have exactly physics model of this structure, but in that case, we can use machine learning like neural network to represent this structural system. Both these two approaches have a benefit and also the limitations. However, recently, a new methodology called the physics-informed neural network gains a lot of interest in different areas. The basic idea of the PIN is try to combine the physics and also the machine learning. Particularly in the practical use, we have some limited data, but we also have some physics, but we don't have a complete physics. So in that case, the PIN can be used to solve this kind of a problem. So before I give deeper into the methodology, I will try to give a brief review of what is the PIN work. This is a typical architecture of the neural network. It can be matched the input and the output with several hidden layers. So the general idea is we try to minimize the difference between the prediction from the neural network and also the measurements, try to minimize the loss. So for the physics informed, we try to add some physics information, which means during the training process, the output should not only fit the data, but also should fit the physics constraints. So in that case, the loss will have two components. One is purely data-driven, another is based on the physics-informed. So by minimizing the loss, we can finally get the unknown parameters of the neural network. And at the same time, if the physics behind is incomplete, which means some unknown parameters in the ODE or the PDEs we need to identify, it can be identified during the whole process. So that's why it is very powerful particularly for the inverse problem. Okay, so this is the basic idea of the PIN. So generally for today's presentation, we try to develop a physics-informed neural network framework, particularly for the structural damage identification problem. And I will use two examples to show the process. And the first example, it is a 3-span continuous beam with cracking. So this is a 3-span continuous beam and under the moving vehicle load. So we can find for the first span and the third span, it has some cracking. So we use a damage parameters gamma to represent the reduction of the flexural rigidity of each span of the beam due to the damage. So the gamma right here is the damage parameters. So if it is equals 0, which means there is no damage, and if it is equals a critical value, which means it is failed. So it can be, generally it can equals 1, or it is a value very close to 1. So we use the damage parameter gamma to represent the damage, and the goal is we try to estimate the damage parameters. So the given information is firstly, we put 3 sensors and each on each span. for the acceleration. So we use, in the numerical simulation, we use some finite element modeling to get the response and add some noise to show the real condition. And also we have some physics. The first physics information is a Gaussian equation, which is a PDE function to represent the structural behavior between like the acceleration and the deflection respect to the moving vehicle load. And the gamma right here is represents the damage, but we don't know the exact value. So we also have the boundary conditions of each support. So based on the sensor data, which is noisy and limited, and also the incomplete physics, so we try to, based on these two components, to determine the damage parameters for each span. So the next step is we try to create a neural network framework for solving this kind of a problem. So for example, for this case, we have 3 spans. So for each span, we will create a neural network. So I just showed the first 2 for the first span as an example. So the input is the location x and the time t. And the output is a deflection of the system. So the first part is we got the sensor data. So the output should fit the sensor data. So we got the loss component respect to the sensor data. And another thing is for the whole domain, each segment, it should satisfy the physics, which means the governing equations. So we got the loss function respect to the physics. And also we have physics between the first span and the second span, which is boundary conditions of the second support, which means both the 2 neural networks should satisfy the physics, which is boundary conditions at the interface between the 2 spans. So right now we can get all the sensor data and the physics loss component. So this is combined loss functions. We got the data and we also get the physics. So by minimize the physics informed neural loss function, we can update the unknown parameters of the neural network and also update the unknown damage parameters. So when we get the neural network parameters, so we can get the neural network. And the neural network, which is a trend, can be used to predict all the response of the system. So which means the 3 neural network can represent this system. So this is generally the framework to be used for this particular case. And this framework can be generalized for different case use. If you change the load condition, you change some parameters, the framework can be also used. And then I will show the results. So we can find the X label is iterations, and the Y label is a parameter of the damage. And the ground is the solid line is the ground truth, and the dotted line is predicting from the neural network. So we can find after several iterations, generally it can close to the ground truth, which means the framework can be used to identify the damage based on the sensor data and also the incomplete physics information. Okay, so this is for the first example. The second example is about the concrete column system with considering the creep. So for this example, it is a 2-column system. And we assume that these 2 columns have different properties. And we have applied load at the top. And we assume that the 2 columns will have the same displacement. So this is the material properties for the concrete. So firstly, we assume that the damage parameters gamma is represent the reduction of the cross-section area of each component due to the damage. We can find for each column the damage is different. And also we put a sensor data, which is a deflection, and we also add some noise to represent the real condition. And also we have some physics, which means the resistant force of each component and sum it together will equals the applied load. And also the displacement of each column should be equal. So based on the physics and also the sensor data, the goal is we try to identify the parameters gamma of each column. And at the same time, we try to estimate the stress and also the strain. Because for elastic condition, it is straightforward. We can get the response very easy. But if we consider the creep or the shrinkage, particularly for a concrete problem, it will be a nonlinear process, which will be complex. But for the inverse problem, we can still using physics from neural network to solve this kind of problem. So before I give into the details of the methodology, I will give a brief review how to get the shrinkage and also get the creep. So I use a B3 model to calculate the creep and the shrinkage. So this figure can show the total strain of the concrete and the load. So this line is the shrinkage strain along the time. And this time the T with prime, which means the time with loading. So all this strain is due to the load. So this is the elastic load due to the applied load. And this is the basic creep. And this is the driving creep. And all these equations can be found in this paper based on the model B3. And we can find for the all the stress induced strain, it is a function of the stress which is applied load. So this is we call the physics, and then we can build a similar framework to solve this problem. So we can find this is a neural network to represent the whole system, and this is sensor data, and these three equations are all the physics. Which means during the process, all the output should satisfy the sensor data and also satisfy the physics. So we got the physics from loss function, which has two components, and with a loop, we can continuously update the parameters of the neural network and also the no damage parameters. So I will get rid of the details, and after several iterations, we can get the result. The first figure is about the identify the damage parameters. We can find after a few iterations, we can find the identified parameters, which is a dotted line, can converge to the ground truth. And also this is about the stress, which is normalized. We can find the red one is for the second column, which means because we consider about the creep and the shrinkage, the stress will redistribute, which means the stress is increased for the second column, but decrease for the first one. But another thing is, again, the pin can get a good result compared to the ground truth. And also, we can get the strain, including the drying creep, basic creep, and also the elastic creep. Basic and also the elastic strain. So we can find again the pin can get a good result and close to the ground truth. This is for the first column and this is for the second one. Okay, so this is all about my presentation, and I will not give. I don't give too much details of the methodology. If you are interested in it, we can discuss later. And so for this presentation, we demonstrate pin work which can combine the physics and the data into a loss function. And by minimize the loss function, we can estimate the unknown parameters. So we use two examples. We can find the pin framework can identify the unknown damage parameters, for example, the cracking, and also it can estimate the response, like the creep strength history, with a high accuracy, even we use noisy sensor data. So that's all about the presentations. Thank you for your listening.